So we just finished laminar flow over a flat plate, and let's go on to turbulent flow. So for turbulent flow, the difference is that there is no Navier-Stokes equation that can be solved, so you just go to experiments. And then you can find correlations from experiments. So for instance, for boundary layer thickness, experiments give delta, which is your boundary layer thickness, over x equals approximately 0.16 over Reynolds number to the 1/7. Okay, this Reynolds number, by the way, Reynolds number is rho u x over mu. Okay, so it's changing along the surface of the plate. And that makes sense because our delta, which is our boundary layer thickness, is growing over the surface of the plate, and it grows proportional to x to the 6/7. And you can figure that out by plugging this Reynolds number in here and multiplying through by x. Okay. Same thing, wall shear stress experiments will give you this equation. You could also then calculate CF, which is your coefficient of friction using that tau. And what you're going to get is about 0.027 over Reynolds number x to the 1/7. So wall shear stress, boundary layer thickness, those are both local values, so they're changing with x. Okay. Drag on the whole side, however, is not something that's changing with x. That's something that you integrate over x in order to figure out what it is. So our drag force per side then is just what we're gonna do is, if you do dimensional analysis, you're gonna get a coefficient of drag over 1/2 rho u squared BL, where BL is that area. And what you get is it's a function of Reynolds number at L and L over epsilon, okay? So Reynolds number just L means plug in L instead of X over here. Reynolds number L equals rho u L over mu. Okay, epsilon is roughness, just like it was for pipe flow. And this time we have L over epsilon instead of epsilon over L. Okay, if the surface is smooth, you can just do some experiments and come up with an equation. And that equation is CD is about equal to 0.031 over Reynolds number to the 1/7. Okay, all of these correlations for turbulent flow don't mean use the laminar flow for the first part of the plate and turbulent flow for the second part of the plate. They're already including the laminar section. So if you find out that it's turbulent at the end of the plate, you can go straight to these equations. You don't even try to use the laminar solutions. Okay, if it was smooth, you can just use this equation. So that was a 1.031. Okay, if you do have surface roughness to deal with, then you're going to have some kind of chart, kind of like the Moody chart. Okay, here is your L over epsilon, so they're big numbers instead of small numbers, but you use it the same way. Reynolds number along the x-axis, that's a log scale, and CD on the y-axis, and that is not a log scale. So watch your scales when you're using this. But basically the method is calculate your Reynolds number, determine at L, determine if it's laminar or turbulent there. If it's turbulent and you have roughness, then you're going to go here, figure out what your CD is. From your CD, you can calculate drag, and that's normally what you're doing. If you need boundary layer thickness or something like that, then you just use the equations for boundary layer thickness. So here's an example. It's the same as our previous example, except it's air instead of glycerin. Okay, so air, a lot less viscous, more likely to be turbulent. So let's try it. What we want to do is, first of all, find delta at the end of the plate. Well, we're going to need Reynolds number. We gotta know, does it get to laminar or does it get to turbulent before the end of the plate or not? So we need to know the Reynolds number at L, at the end of the plate. Rho u L over mu. And if I plug those in, I get 4.17 times 10 to the 6th, which is greater than 5 times 10 to the 5th, which is our critical Reynolds number. So it is turbulent at the end. Okay, which means we're going to use our turbulent equations or our chart that's like the Moody chart. So part A says find delta at the end of the plate. So delta over, what we had was delta over x was about equal to 0.16 over Reynolds number to the 1/7. Well, we want to find it L. So we're going to say delta over L is about equal to 0.16 over a Reynolds number L to the 1/7. Okay, we already calculated our Reynolds number. That's this. And so just plugging into this, we're going to get delta is about equal to 45.3 millimeters at L. Okay. So B, drag force on one side if smooth. Okay, so what you do is figure out what your CD is, and if it went turbulent and we're talking about smooth, we can just use that equation, 0.031 over Reynolds number at L to the 1/7. Okay, it is to the 1/7, correct. Yes. And that comes out to be about, well, I didn't calculate that. Drag then comes out to be about drag, our coefficient of drag is equal to drag over 1/2 rho u squared times the area, B times L. All right, so what we can do is just equate these two, and what you get is drag is about equal to 0.031 times 1/2 rho u squared BL over Reynolds number to the 1/7. Comes out to be about 4.1 newtons per side. All right, that's part B. Part C then is assume a roughness. Epsilon is 1.25 millimeters. Okay, L over epsilon then is going to equal our 2.5 meters over 0.00125 meters. Comes out to be 2,000. All right. So what we need to do here, since we have roughness, is we've got to use that chart, figure 7.6. Okay, and if I go back up to 7.6, I'm going to look for 2,000 for my L over epsilon, which I got here. Reynolds number was about 4.2 times 10 to the 6th. So that's going to be somewhere in this range, okay, probably around there. And then I'm going to go straight over, and I'm going to get about 0.007. So my CD is about equal to 0.007, and then my drag is about equal to 1/2 rho u squared BL times that 0.007. Comes out to be 8.2 newtons. All right, that's it. Go ahead and finish the quiz, and I'll see you in class.